Quantum rewinding for many-round protocols. Introduction. Succinct arguments allow a prover to convince a verifier that the statement X belongs to a language L, the communication shorter than the witness length for the corresponding relation. Succinct arguments have become a cornerstone of modern cryptography and fueled the development of many real-world applications such as verifiable computation and anonymous cryptocurrencies. Recent years have seen an explosion of new constructions of succinct arguments based on a variety of cryptographic assumptions. However, the advent of quantum computation poses a significant threat to these advancements. On the one hand, Shor's algorithm forces us to transition to cryptographic systems based on post-quantum assumptions, such as the hardness of the learning with errors LWE problem. On the other hand, some known techniques to prove security of cryptographic protocols no longer apply in the post-quantum regime due to the fundamentally different nature of quantum information. Most notable are rewinding techniques, which are ubiquitous in security proofs for succinct arguments. In a rewinding proof, it is argued that an adversary that succeeds on a single random challenge with high enough probability must succeed on multiple challenges. This classically intuitive idea fails in the quantum setting because measuring the adversary's response to one challenge causes an irreversible loss of information, which may render it useless for answering other challenges. An important family of succinct arguments are interactive protocols based on the recursive folding technique, also known in the literature as bulletproofs. Leveraging algebraic properties of cryptographic schemes, bulletproofs-like protocols can achieve much smaller proof size than PCP and IOP-based succinct arguments, while retaining the benefit of a public coin setup. Unlike PCP and IOP-based arguments, however, the original bulletproofs constructions are not post-quantum secure, being based on the hardness of the discrete logarithm problem. This has motivated a line of work that aims to design post-quantum bulletproofs. While these works do not rely on cryptographic assumptions which are quantum insecure, their analysis of post-quantum security is only heuristic in the sense that soundness is only shown against the classical adversary. Motivated by this state of affairs, we ask the following question. Can we prove post-quantum security for bulletproof-like protocols? Known techniques for rewinding quantum adversaries do not appear to generalize to multi-round challenge response protocols, let alone to logarithmic round protocols like bulletproofs. Thus, answering the above question requires us to develop new quantum rewinding techniques or results. In this work, we show that the case of recursive many-round interactive protocols is knowledge sound against quantum adversaries. As a special case, we established that lattice-based bulletproofs protocols are post-quantum secure, assuming the quantum hardness of LWE. Loosely speaking, our main result can be restated as follows. Theorem 1, informal version of Theorem 4, assuming the quantum hardness of ring LWE problem, lattice-based bulletproof protocols are knowledge sound against quantum algorithms. Our main result is obtained by developing two technical contributions of independent interest. Fault collapsing hash. We show that the lattice-based hash function satisfies a strong collapsing property. Intuitively, we show that hash A remains collapsing even when the Ka is compressed via linear combinations of its columns, with the coefficients being short units in the base ring. This fault collapsing property can be based on a variety of computational assumptions, including the ring LWE assumption, or ring W assumption. Quantum tree rewinding. We develop a new quantum rewinding technique that allows us to extract from multi-round interactive protocols with certain collapsing and recursive special soundness properties. Our method combines the state repair procedure with a probability estimation step that determines the success probability of the adversary on a given subtree. Combined with the collapsing property above and the recursive special soundness of bulletproof-like arguments, this establishes the post-quantum security of these protocols. Related work. The witness folding technique for constructing succinct arguments was first introduced by Bootle et al. And later optimized by Bunz et al., who called their protocols bulletproofs. The term bulletproofs is now used to refer to a family of succinct arguments with certain recursive structure. The early bulletproof protocols prove quadratic relations of exponents of elements in prime-order cyclic groups, and their soundness relies on the discrete logarithm assumption over these groups. Lai, Malavolta, and Ronk generalized the folding technique to prove quadratic relations over bilinear pairing groups under a variant of the discrete logarithm assumption defined over these groups. As the discrete logarithm problems can be solved by Shor's algorithm in quantum polynomial time, none of these protocols are post-quantum sound. While it is necessary to consider nonlinear relations to obtain an argument for NP, Atema and Kramer showed how to linearize the nonlinear relations using secret sharing techniques and apply the folding technique to compress the argument for the linearized relations. Although their protocols for proving linear relations over groups are in fact unconditionally sound, they are trivial in a quantum setting because the relations that they prove are in BQP. Bootle et al. Adopted the bulletproofs folding technique to the lattice setting, giving a succinct argument for proving knowledge of the witness of a short integer solution SIS instance, i.e. a short vector x satisfying a times x equals y mod q of the mth cyclotomic ring with m being a power of 2. The protocol, however, has large slack. The knowledge extractor is only able to extract a short vector x satisfying a times x equals 8 to the t dot product y mod q, where L equals 2 to the t is the dimension of the witness x. Albrecht and Ley revisited this protocol and reduced the slack from 8 to the t to 2 to the t with a careful choice of the challenge set R. They further eliminated the slack in the case of prime-order cyclotomic rings, i.e. when M is a power of a polynomially large prime. Atema, Kramer, and Co. improved the soundness analysis, reducing the knowledge error from O log L to log L, which is tight. Bootle, Chiesa, and Sotiraki proposed the abstract framework of sum-check arguments, which captures all bulletproofs-like protocols, particularly lattice-based ones mentioned above. Although lattice-based bulletproofs for proving SIS relations are shown to be unconditionally sound against classical provers, the security proofs implicitly assume that the success probability of a prover remains unchanged after rewinding, which is generally false in the quantum setting. Organization. In Section 2, we give an overview of our technical results. In Section 3, we recall standard preliminaries. In Section 4, we recall the notion of public coin interactive arguments and introduce the notions of recursive special soundness and last round collapsing. In Section 5, we show that protocols satisfying these properties are also knowledge sound, even against quantum provers. In Section 6, we study the collapsing properties of hash function families implicit in lattice-based bulletproof protocols. In Section 7, we build upon the results of Section 6 to show that lattice-based bulletproof protocols are recursive special sound and last round collapsing and hence knowledge sound, even against quantum provers. Technical overview. We gave a brief overview of the main technical steps of our work. Before delving into the details of our analysis, we summarize the main conceptual steps of our proofs. Step 1. We formalize a family of public coin protocols sigma that satisfy two main properties of interest, namely recursive special soundness and last round collapsing. Step 2. We describe a new quantum rewinding strategy that allows us to extract a witness from any recursive special sound and last round collapsing protocol of the above defined family. Step 3, we show that the lattice-based hash function hash A of x equals A matrix A times x is fault collapsing, assuming that the ring LWE problem is intractable for quantum algorithms. Step 4, assuming the result from the previous step, we show that lattice-based bulletproof protocols are recursive special sound and the last round collapsing. The remainder of the technical overview will be split into two parts detailing step 1 to 2 and step 3 to 4 respectively.